Welcome back to Basic Electronics. One of the major applications of a BJT or even other transistors is amplification. In this lecture, we will look at the basic idea behind amplifying a signal with the help of a BJT. We will then look at a simple BJT circuit which can be used as an amplifier by suitably selecting the resistance values. Alright, let us begin. We are now going to discuss BJT amplifier circuits, and let us begin with the basic idea behind a BJT amplifier shown here. Here is an NPN transistor, a voltage source connected here, a voltage supply VCC, and there is a resistor RC. When we replace this NPN transistor with its equivalent circuit, we get this circuit here, assuming of course that the transistor is operating in its active mode or the linear region, and therefore we have a diode and a current controlled current source. Let us look at the plot of IC versus VBE. Now VBE is the same voltage as the voltage across the diode here, and therefore IE versus VBE is going to look like a diode IV curve. What about IC? IC is simply proportional to IE, equal to alpha times IE. In fact, IC is approximately IE because alpha is generally close to 1. And therefore IC versus VBE is also going to look like a diode IV curve, and that's exactly what we see over here. Up to about 0.6 the current is very small, and then it takes off and becomes appreciably large. Let us see what happens if we apply a time dependent voltage at the base, which is the same as VBE. So that is VBE as a function of time. So we have a sinusoidally varying VBE here. It is not a sinusoid with zero average value. It has got some DC value around which it varies. And as VBE varies, the collector current also varies. For example, this maximum VBE corresponds to this maximum IC here, and the minimum VBE corresponds to this minimum IC here. And of course, there is a variation from the maximum to minimum in between. So let us summarize. In the active mode, IC changes exponentially with VBE, as we just saw. IC is given by alpha f times IE, and IE in the active mode is IES times exponential VBE over VT. This one of course is too small. So that is how IC varies. Now the output voltage which we take at this node, at the collector right there, is VCC minus this IC RC drop. And since IC is varying with time, VO is also going to vary with time, and the amplitude of VO can be made large. That is IC cap times RC, where IC cap is the amplitude of the IC waveform. So that is from there to there. And we can arrange the resistance value and the VCC supply value, etc., so that the amplitude of VO, that is IC cap times RC, can be made much larger than VB cap. What is VB cap? That is the amplitude of this sinusoid here. So our input voltage has an amplitude of VB cap, and the output amplitude can be much larger, and that is how we have an amplifier. So that's the basic principle of BJT amplifier. One very important point to note here is that both the input VBE and the output voltage VO have a DC component. For example, VBE is not varying around 0 here, it is varying around some DC value. Similarly, IC is not varying around 0 here, it is varying around some DC value. And VO also will do the same. So this is a very important point, and let us make a note of that. We now want to look at the effect of the DC component of the input voltage VBE on the amplitude of the output voltage. So here is VBE and that is IC, similar to what we had in the last slide, except we now have VBE going from 0.6 to 0.7 volts, and that is our IC versus VBE. We are going to apply two voltages, two input voltages, both sinusoidal, 1 and 2, and their amplitudes are identical. The only difference is that their DC components are different. So this voltage 1, input voltage 1, is centered around this DC value, whereas input voltage 2 is centered around this DC value here. We can map these input waveforms 1 and 2 to the collector current versus time plane, and that is what we have done here. And we notice that there is a substantial difference between the amplitudes for the second waveform and the first waveform. And this change in amplitude between these two cases is not because these amplitudes are different. In fact, these are the same. It is entirely because these two waveforms differ in their DC values. And if IC of t has a different amplitude in these two cases, VO of t will also have different amplitudes. That is because the amplitude of VO is simply the amplitude of IC times RC, or VO cap is IC cap times RC, as we saw in the last slide. So let us note down these important points. The gain, that is the amplitude of VO versus the amplitude of VBE, depends on the DC or bias value of VBE, the value around which, the DC value around which these input waveforms are centered. That's called the DC or bias value of VBE. Now in practice we might say that this looks better than the second waveform, and therefore let's choose the DC value to be this one rather than this one. But it's not really possible to set the bias value of the input voltage to the exact desired value that we would like, for example 0.673 volts. We simply don't have that kind of a voltage supply. And even if we could set the input bias as desired, for example by some means we managed to set it to that value, there is still a problem, because there is a device to device variation, there is a change in temperature, etc. And all of these things would cause the gain to change, and so therefore we are building the circuit with a certain gain in mind, and after we build it, we will find that the gain is something else, and we would not really know what exactly went wrong. Clearly, we need a better biasing method. This kind of extreme reliance on the exact DC value is not really helping us. Finally, let us note also that biasing the transistor at a specific VBE is equivalent to biasing it at a specific IC, and that is simply because there is a mapping between the DC value of this input curve and the DC value of the IC versus T curve. So that's an important observation, and in fact we are going to use that when we study amplifiers. Before leaving this slide, let us look at this point in more detail. What exactly do we mean by device to device variation? What we mean is this curve, which is IC versus VBE, would change from device to device, and that's because there are variations in the doping densities or geometry, etc. of devices. So instead of this curve, suppose we had a different curve, let's say something like this, that would change the mapping between the input and the output, and we will get an entirely different collector current versus time profile. Similarly, if there is a change in temperature, for example, you are expecting the circuit to operate at 25 degrees and it's actually operating at 40 degrees. Then what happens? Then this curve is going to shift. It turns out that at higher temperatures this shift will be in that direction. And once again, because of that, the same input voltage will now result in some other IC of t. And that is why, even if we could set this input bias exactly as we wanted, there is still a problem, and calling for a better biasing method. Let us consider a more realistic BJT amplifier circuit, this one, in which we have added this base resistance RB, and that helps to limit the diode current here. If the diode current increases, then this voltage drop also increases, and therefore even if Vi is large, like 5 volts, the base emitter voltage is still limited to something like 0.7, and thus the transistor is protected. If the current became very large, like amperes, then the heat generated in this device would destroy the transistor. So this is a much more realistic amplifier circuit as compared to the last one. And let us see how this one works. We have plotted the IC versus VCE for this transistor. What is VCE? VCE is the same as VO. That is what we have mentioned here. And here is the load line that is imposed by this resistance RC here. And we have seen this earlier. Just to revise, when the collector current is 0, VCE is equal to VCC, and that should be obvious also from this figure. If there is no current here, then VO or VCE is the same as VCC because there is no voltage drop there. On the other hand, if VCE is 0, if this was 0 volts, then this current would be VCC minus 0 by RC, that is VCC by RC. That is what is shown over here. And for the transistor, we have this family of curves, one corresponding to IB1, one corresponding to IB2, and so on. And IB2 of course is greater than IB1, IB3 is greater than IB2, etc. When Vi is less than 0.7 volts, the base emitter junction is not sufficiently forward biased, and therefore this diode current is negligibly small. No voltage drop here across RB, and VB is then the same as Vi. If the diode is off, the transistor is in the cutoff region as mentioned here, and therefore there is no collector current. VO gets pulled up to VCC. So VBE is then the same as Vi, which is not yet 0.7 volts, and VBC is Vi minus VCC, and that definitely is a reverse bias. Where are we in this figure? the base current is 0, so that means there is one IC curve coinciding with the x-axis here, and that is where we are. The operating point then is the intersection of this IC VCE curve and the load line, that is right here. So our VCE is the same as VCC. Where are we in this figure? We have not yet reached 0.7 volts or the turn on voltage for the transistor, and VO is then VCC, which is 5 volts here. This is VI and that is VO. When VI exceeds 0.7 volts, then the BJT turns on and it enters the linear region. What do we have for IB then? IB, this current, is VI minus this voltage drop, which we will say is about 0.7, divided by RB. So that is VI minus 0.7 by RB. And as VI increases, IB also increases, and therefore IC also increases. Now if IC increases, this current increases, what happens to VO? This voltage drop increases, and therefore VO, which is VCC minus that voltage drop, will decrease. So that is what it says here. VO, which is equal to VCC minus IC times RC, starts falling. So let's see where we are in this figure now. So now we have a finite IB, a non-zero IB, and the IB value is increasing as VI is increasing. So we are now moving from this curve to that curve to that curve and so on. And as a result, the intersection of the load line and the ICVCE curve also goes on changing. So this was our output voltage earlier. When the base current is IB1, the output voltage is here. When the base current is IB2, the output current is here. Sorry, the output voltage, and so on. So the output voltage starts falling for sure, and that is also apparent in this figure. VI is increasing here, IB is increasing, IC is increasing, and therefore VO is falling, and that fall can be seen right here. As we keep increasing VI, the output voltage VO will reach VCE sat at some point. What is VCE sat? It is the value of VCE in the saturation region. So it's between 0 and 0.2, and we often take it approximately as 0.2. And when that happens, the BJT enters the saturation region, that is both the base emitter and base collector junctions are now forward biased. What is happening in this figure? Our VI is increasing, so our base current is also increasing, and the intersection of the ICVCE curve and the load line is also therefore shifting. Now here we are still in the linear region, linear region, linear region, linear region, but for IB equal to IB5, we now enter the saturation region. So that is how the transistor has entered the saturation region. And what happens if we increase the base current further? Let's say we are on an IC VCE curve here. That curve would go like that, and then in the saturation region it will come down, and again the intersection would be somewhere there. And what we just discussed also reflects in the VO versus VI curve. This was cut off. Then as we kept increasing VI, the transistor entered the linear region, and finally it reached the saturation region, and then it stays in the saturation region. To summarize, we have looked at how a BJT can be used for amplification. We have also seen a simple BJT circuit that can work as an amplifier. In the next class, we will continue with this simple circuit and then identify important issues which must be considered in building a practical amplifier. That is all for now. See you later.